right, so problem number 3, right? Homework 1, right? Um, just to let you know, right? Um, this is largely coming from Yoo Hyun Kim's homework, right? Um, the student sent out his or her homework way earlier than the other guys. So I looked at it and then incorporated many of his parts into this demonstration, right? And then double checking what's going on there, and then making sure the results are what I intended, right? We want to make sure about it. So anyone who wants to participate, I mean, the participation grade will be up if you send me the codes earlier, and then we can use it in our class like this. So let's utilize that opportunity, okay? Anyway, so PB, right? I'm going to create a PB data, PB ratio data, starting with this price to book for Kospi stocks, right? And then once I import it, there will be a period variable which has first quarter, second, third quarter, and semi-quarter kind of things, the string variable that tells me about the periodicity. Then we will change that into numerical values, like the numerical string values, right? It's actually a string, um, which looks like month and then the end of the month's date. So March 31st for the first quarter, and then June 30th for quarter, right? Why is that the case? Because 100% of Korean companies, their fiscal year end is December. And then uh, which makes our life easier, because American companies, like 20% of the companies, they have fiscal year end in some different months, like January or November or whatever time, like June, which makes our data work crazy. But over here in Korea, it's very simple. So we can just switch it into month end of each quarter like this. And then we know we have the fiscal year numbers there, and we will connect these two into a string, okay? And then there may be some empty space in between when we connect these two, so we're going to eliminate those things with some procedures, data steps as follows. Okay, let's see. So yeah, yeah. That's this procedure, right? And then character. As character. Start from fiscal year. You know, this is a numerical variable, but we're going to convert it into character so that we will be later be able to concatenate this fiscal year and the period together. And then finally we will end up with some strings with numbers that we can convert into numerical variable later. Okay, so let's see. Make sure this is character variable, and then maybe we should open up and see what the heck is going on over here. You see fiscal year and then the period. Whenever you see these kind of things, you look at this box and then pay attention to whether this number is in the front or back, right? It is tilted towards the front or left hand side, which means it's a character, okay, instead of number. If you look at FIR, this is number because it is tilted towards the right hand side, right? Later we will merge, concatenate or attach FIR and then period together, okay? So that it will be one string value, okay? And then you see the others are correctly imported. Yeah, you're right. Then move on to the next, which is Um, paste, right? Paste is concatenating two, right? FIR and then F year and then period together. Paste it. And then check out the class of it, which is character again. Just open up the data one more time. Right? You see it over here. These two columns attached with each other, attached to each other. But uh-oh, there is an empty space in between. Interesting. How do we eliminate this thing so that it will look more like a number, okay, representing the date of quarter end? That's this guy, G sub, right? G sub function, okay. And then G sub function, let's see over here. Right, now it looks a lot more like the date figure, but it is a string. You see it is tilted towards left, right? So we have to convert this guy as date value, okay, date value. Now what? And then notice SEQ market cap are recognized as character, not numeric. This is because we have some commas inside. Market cap, right? Did you notice that? It is character, and we need to replace commas with nothing at all. Okay, G sub, using it again. Okay, and then you need to familiarize yourself with text functions as you do this kind of our courses, right? Regular expression kind of things. You have to familiarize yourself, and then from character we are going to convert into numeric for SEQ variable and market cap variable, right? Like this, yes. And we need to switch the FY year quarter format into date format, as I said before. Okay, so date one, yeah, as date, as that date, it converts it, right? And then once we do this, right, let's check out our good old friend, our data. Now it looks like this, right? And if you bring it, yeah, column, right? You see market cap, right? And then SEQ, they are numerical columns, right? So we are happy about that. And we need to drop third to seventh columns, right? Remember, there are a lot of missing values in NAs in the SEQ and market cap. We want to make a quarterly frequency data, which necessitates us to find a way to attribute the values of most recent past to current quarter's values. That's na.locf function. Last observation carried forward. Okay, last observation carried forward. Okay, so PB, start from PB. What does this mean? Well, the row and column, row comma column, column wise, drop, minus means drop, 3 to 0. Okay, columns, and then that's PB1. Okay, creating PB1. And then let's do it first. PB1, let's take a look. Now this guy looks like this. Symbol and name and fiscal quarter. Okay, period by period. And then the next one, starting from PB, we are just eliminating the first column. So PB, symbol column, we are just deleting this one. Okay, right, and then we're going to let's see, okay, PB and open again. You see the ticker symbol gone, and then we want to delete these guys because what we need is these three, right? So 2 to 4 is eliminated. Okay, and then market cap, yeah, will be second column of the remaining set will be deleted. That's market cap. So let's open up the market cap over here. It shows this guy, right, like this. Okay, and then SEQ, well, that's this guy, right? SEQ, right, like this. Okay, then switching row data into column-wise data by the name of the company. Okay, by the name of the company. Here we are going to use pivot underbar wider function quite often. Why? Because we have what? Okay, I can write it over here. So one company, Samsung company, right? And then the other, let's say that's Hynix company data for the same period. And then the third is, let's say, what is it? This Celtronic, right? The same period repeats, but it's different companies, right? That's this market cap or whatever PB kind of or SEQ data is about, right? It's just row-wise, it's long, but we want to make it a, how do you say, column by column by column data, where the column header is the name of the company. Okay, as if each variable, right, name is the company name. Okay, so we want to do it like this so that it will look like that, H and C, and that is what pivot wider is doing it. Okay, pivot wider. Why do we do this? Because we want to create that orange kind of the time series graph of 200 different PB ratios, right? So let's do it. Okay, MKT, yeah, market, right? So switching row data into column wise by the name of the company. Okay, MKT, let's see, where are you? There you are. It has 160 observations and 201 variables. One variable is the quarter end, right, date, but the remaining are those company names. Yeah, sorry, this is Korean words, but you can convert it later into English, okay? But anyway, so filling in NAs with the most recent past, okay, value of SEQ using LOCF function. Well, what do we do? First, pivot wider. Okay, pivot wider. We will use it, but wait a minute. If we open the MKT function again, okay, 삼성전자. And the thing is, we used to have missing values of NAs before, and then 60 missing, and then 64 missing, 81 missing. But we replaced those missing values with the previous ones. Okay, so that's LOCF, LOCF function. Okay, so we are going to do the same thing for SEQ data. First, we have to pivot wider, and then right, we will do that. Okay, but before that, SEQ, whenever it is missing, no. The first row of SEQ, we just replaced it with minus 100. Okay, why not 0? I don't know. Okay, That's what the Yu-hyun tried, okay? But minus 100, he tried it. 0, you can also try it. But yeah, that doesn't make too much difference anyway. So let's do it. And then SEQ, how does it look like? Yeah, here we are. And you see, voila, 100 minus is showing up. For this part, we are going to later delete or something, okay? But the remaining part, you see those NA a previous value attributed. Yeah, you can see that. Reorganizing the data into original format, you have to do it, okay? Pivot, instead of wider, pivot longer, okay? You have to do it because we want to compute the what's that? The PB ratios, right? PB ratios in a long data format. So for that part, we run it like this, and then pivot longer. We create, yeah, MKT cap 1 variable value, the matrix, okay? MKT1 looks like this, right? And then the same date, different companies, yeah, going further down like that, okay? So that is it. And then SEQ, we do the same, and then SEQC will be created like this, okay? Yeah, like that, okay? Right. And then what we do? Merge these two data sets so that we would be able to compute PB ratio. Okay. Yeah. So first we create price to book and then merge with PB1. What was PB1? Do you remember? That was this guy. Okay. We had a whole bunch of symbols and then 삼성전자 이름 names, right, in Korean, and then quarter date. Okay, there's no PB ratio at all. That's something we have to calculate. Now, so for that part, first merge with market cap 1 and SEQC, and then merge the resulting part with PB1. The resulting data name will be price to book. Price to book over here. Okay, now you have market cap and SEQ, right? Good to go. Yes. Now, what? The creation of PB ratio, okay? Removing market cap equals 0 data. Yes. And then the price to book ratio, yeah. Whenever SEQ is 0 or minus, yeah. Replace it with NA, okay? I would, okay? In fact, I would do it differently, okay? If in fact, I would do it differently. If it is less than or equal to, whenever SEQ is negative or 0, replace it as 0, as NA, okay? So let's see what happens to the price to book ratio data. Price to book ratio, and then SEQ, NA, right, okay? For these, well, and then, right, so NA. All positive SEQs remain, okay? So I'm happy with that. Removing shareholder equity values, yeah, you don't need this procedure, so I will make it like this, and then there you compute, okay, price to book ratio, PB ratio, right, based on market cap and SEQ, right, and then, yeah, right. Now, whether it is 0 or not, you don't need to worry about it, okay? Because price will be always slightly positive, and then what is that? SEQ being 0 or negative, I dropped it or treat it as NA, right? So that's this. Now what? We have price to book ratio equals to infinity. If that explodes, right? That number explodes, then treat it as NA. Okay. You don't need to worry about it because I dropped those cases where the SEQ is 0. Okay. And removing negative infinite number, blah blah blah, you don't need it because I already did that. Okay, so no need to worry. Yes. I want to check out the distribution of PB ratios. So I run a histogram. Looks like this. Holy cow, you are screwed. Why? This is highly positively skewed, right? Okay, fine. You can see that it goes even to almost like 100 or something. Crazy. Um, yeah. Okay. That's something we'll have to worry about. One is truncation, right? Dropping those extreme valued observations. Another is Windsorization. That's replacing those extreme 1% or 5% observations with the threshold value of top 5% or top 1% or something like that. Okay? Because those 1% may occur over here, or 5% may occur over there. Okay? Once you reduce it like that, Windsorize, then the distribution may look very different. Okay? So that's something we have to think about. Either truncate it or Windsorize it. Another thing you can think about is doing some log transformation. Okay? Taking log, natural log of it. Okay? But let's see. Okay? Yeah. And then here PB ratio. Okay? Yeah. Want to check out the distribution? Yeah. Let's see. Maximum of price to book ratio. Yeah. 96 times. Mean is 1.42. And then the standard deviation 2.3, 2.4 almost, right? Beware of extreme values, beware of negative PB ratios and things not meaningful, right? Better to drop it. I did it. Removing outlier PB ratios for better analysis. You can do it like this. So this is truncating at top 97.5 percentile, right? So let's do that. Okay. And then the next is truncating at the bottom. But do we need that? Is a serious question. And I don't. Why? Because we already dropped those negative guys, which is supposed to be on the extreme on the other side, right? So we already did it. So we don't need this part. Okay? And then let me draw a histogram once again after truncating this PB ratio at top 97.5 percentile, right? Yes. Now it looks like this. Okay? So that's one thing that you can play with. You see the top happens at 7%, right? 7 times, right? That's an interesting thing, you notice. Another thing you could try is a log transformation. Maybe should I try it? But maybe later. Yeah. Anyway, so that's one thing you would try. And then Removing outliers, yes, 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 yes. Why should it be 97.5 percentile? Why not 5 percentile? Or why not 1 percentile? It's up to you, okay? You can try everything, okay? We call it robustness check, okay? Don't hang up onto, don't get hung up onto one measure only, one way only, okay? If you truncate it at 1% level, try it with 2.5% level, try it with 5% level, and then see if your results or conclusion is robust, no matter which percentile you choose, okay? But in the interest of time, I'm going to just stick to this 97.5 percentile truncation, okay? And then removing outliers, that's 3.6. Obtaining mean PB ratio of the specific year and mean PB ratio overall period. Yeah, so price to book ratio, we're going to create PBC, right? PBC based on price to book data set over here. Okay? Remember, all the PB ratio after truncation is still in price to book data. And then we're going to drop third to fifth column of it, so which means like we're going to live with the first two columns of it. Okay, fine. Okay, fine. What is it? So much so that we have to do it before you say really okay. Over here. Okay. 1, 2, 3, 4, 5. What we need is this guy, right? And then we're going to play with this one. So that's why. And then pivot wider function tells us that we want it to be company by company, right? And then we want to take the mean of it. Wait. PBC. We're going to create a data set called PB mean. And then, so let's see. Yeah, PB mean is created. PBC is this guy. Row Y, the column wise data, like this. Good. And then PB mean. Always wonder. Open it up and check it out. Good. Right. All those means. Right. Yep. And then PB mean is nothing but PBC that you created, identical data anyway. And then out of PBC, okay, we're going to create PBR data, which is eliminating the first column. So PBR, PBC, first column eliminated, and then we're gonna create a PB mean, overall mean variable, which is COSP 200's mean PB ratio throughout the history. Okay, 200 stocks throughout the history, the mean. Okay, and then let's see what happens. Yeah, the second row over here says for each time point. Remember, in PBR dataset, we have all different columns of PB ratios of the companies for the same period. So for each period, we want to get the mean PB ratio, which will be time varying, right? So PB mean and mean PB ratio. Let's see PB mean data over here. It has 203 variables, columns, and then 160 observations. All right, fine. So you see, as you go to the rightmost column, you're going to see some interesting thing over there, which is, yes. The second rightmost column is overall mean, which is time invariant. It's not changing because this is the average of the whole data. Okay? one number. Whereas the rightmost column is mean of all time series, the different time points, right? So that's the thing, okay? But anyway, so that's that. Let's, yeah, yeah, yeah. That's that. Now, do I have to resort it? Let me create these sets once again because I am afraid I sorted it without any thoughts. So I'm creating it again, and then for mean PB ratio, okay, mean PB ratio values, right? The average PB ratio for each quarter, right? First three observations we will replace it with NA, treating it as missing values, and then mean PB, right? PB mean. We are going to drop second to the 201st columns so that we will be left with the historical mean and then the what is it, the time point wise average mean. Okay, so let's do it. Okay, so PB year mean will be like this guy. PB mean, let's go to this one. Yes, we have only 3 columns, which is date and then overall mean and then mean for each period. Okay, then what? Well, like this. All right, PB year mean will be like this, and then PB overall mean, OVR mean, right? Here, it will be what is that? Overall mean, the time invariant average of the whole period. You can try median somehow, but I will leave it as your challenge question. Anyway, so you have this necessary averages, right? We want to create a table or chart, okay? For that purpose, let's specify the chart format, and then fiscal year quarter, right? This we are converting data values into numeric value for plotting purpose. Starting from first observation to all the way down to 160, right? Then PBC quarter, yeah, right. And then this has to be all numerical or this, right? Yeah. And then A matrix is constructed, okay? It's gonna be like this from 4 to 160 by 4. We're going to use matplot, and then using heat colors 24, right, degrees, price to book ratio, and then axis will be defined from 1981 to 2020, and the axis starts from y-axis starts from -5 all the way down to 8. But I would say we can just start from 0 to 8. But let's see what happens, okay? And then we're going to plot price to book ratio of all the things, right? For all the things, PBC, right? Right. And then PBY mean, historical average, and a monthly average, all these things in the same chart. So let's see. Abracadabra. Yes! and it looks like this. Zoom it. Yeah, looks like this. Okay, so even though I defined the y-axis to be like -5 to 0 to 8, it automatically starts from 0 and then going up, right? Interesting thing is, by clicking the zoom button, I can widen it like this and then see it more precisely like this. Okay, and then you see historical average, okay, of PB ratio 1.4 or something was that, and then you see the the quarter by quarter, right? Average PB ratio fluctuates like this, right? Are we in a bubble or not? We are over here, right? Strangely enough, or to my personal taste, right? Strangely enough, we don't seem to be in a bubble too much. Okay, fine. Um, then we can check, right? Then we can check whether those period that we experienced some bubbles, their PB ratio was above this average. For example, before financial crisis, like this time, 2007 and 6, yeah, definitely it was, right, above historical average. And in 2008 we dipped into crisis. Over here you can see it is plunging below average, right? And then it bouncing back like that. And if we go down to 1998 and 7, 96, 7, this is East Asian financial crisis, right? And then 1998 and 7 and 1999 it was popping up a little bit, but it's bouncing back. 99, 98. Yeah, I mean this was the time point 6, 7, 8, 9, right? 7, 8, 9. So 7 and 8 it was bottom. 9 up again, and then 2000 was going down, right? Anyway, so you can see those matches with the bubble, reasonable match with bubble and crash like this, PB ratio average. By the way, average is driven more by extreme values. So more robust measure will be median values, right? But I leave it up to you for challenge exercise. And the one thing before I forget, you see the PB ratio was dipping in the beginning of this year, March, right? Obviously, COVID-19 effect, it was showing up like this, right? So that's that. Now, export the mean table to Excel to see if we are in bubble or something. This is what I just added, right? Here is an exporting function, okay? If you have trouble generating table in R, don't stop there and say, I can't do anything, Andy. You screwed me up. No. Do something, right? Do something at least so that you will be able to do it. This is just like your job, right? So your boss wants a graph, does not necessarily want it in R, right? Of course, R will be better for grading purpose, but yeah, throw it into Excel and then graph it yourself. That's this guy, okay? I already installed this package called the Write Excel, so I don't want to run it, import it this time, but I'm just exporting it. Yeah. Right. So in Excel spreadsheet, you can open up and generate your table in your own way. Okay? Nobody said that you cannot do it. You should, try everything. Okay. Good. And then homework number 4. Okay, homework number 4, it's about what? Regression of your PB against growth expectation. So here, okay, I will focus on, okay, quarter of September, end of September, okay, the value, because the previous value is attributed to September 9th. I mean, the important thing is the month over here as of the quarter. The previous value of June should be attributed over here. That's why PB2 is generated with this function over here, filtering option, right? Whichever that satisfies this condition. Okay, fine. And then PB2, okay, PB2, let's check out before we move on further. PB2, hello. Yes. And then you have how many observations? 200 observations, and then 6 variables. 1, 2, 3, 4, 5, 6. Yes. Right? What you need is this guy, PB ratio, and then you need to attach or merge with growth data, growth rate expectation data, right? That, right, we're going to import it from this, right? And then we're going to call it NIGE, net income growth expectation, right? So read CSV and then yeah, yes. Summarize it. It has symbol name and G underbar EPS, growth rate of EPS. And you are in trouble because this is in character value instead of numerical value. So we have to convert it as numeric, right? And remember, this is in percentage figure, whereas we want it to be in decimal figure, just to be common, right? So we do it this way, divide it by 100. Yes. And then we will create a data set called PB regress by merging PB2 and NIGE. And the merger key should be, the reference in merging should be the symbol, right? As long as you have the same symbol, merge it, okay? So let's see PB regress. Yes, PB regress. Right. Now you see these G of EPS showing up over here with some missing values over there. Naturally, those 적자 전환 or 흑자 전환, those character values are gone. NA, nah, right. Name.y, because it was coming from both data sets, X and Y. We're going to drop one of them. Anyway, so that's that. And summary of this guy, yeah, PB regress. And then we are going to run some histograms. Yeah, we are happy that G of EPS is numerical by now. But as we run the EPS growth rate histogram, we are again, feeling some trouble over here. It's highly skewed to the positive, right? Number 2, EPS growth rate, right? By the way, 적자 전환 or 흑자 전환, this kind of things I told you before, switching from positive EPS to negative EPS, you cannot play over here. It's going to be meaningless in our exercise. Again, negative EPS to positive EPS, meaningless, right? Those numbers cannot be used. So in those cases, these values were already in string, 적자 전환 or 흑자 전환 kind of things. So we don't need to worry about it. But here, what we have to worry about is the skewness, right? Skewness. Okay, fine. How do we take care of it? Okay, histogram. And then the PB ratio histogram again. Okay, over here. Yeah. We may take a log of it. Okay, we may take a log of it, of PB ratio like that. For growth rate, we don't take a log of it but let's see what we can do. By the way, if you take a log of it, okay, PB ratio, what happens to the distribution? The histogram of log of PB ratio looks like this. It's more of a symmetric, okay? More symmetric than skewed, okay? So that's another thing we could use later on. Maybe useful, maybe not, but that's, at least it is symmetric, so we are, happier. Plotting regression line and confidence interval. Okay, here we filter out. Okay, what I do is because of the extreme values of EPS growth rate that you see before over here, highly skewed EPS. Okay, this is one arbitrary hand-waving way of doing it. Okay, strictly speaking, you want to do some truncation like what we did before, above 97.5 percentile, drop it. Okay, and then do the regression with the remaining part. Okay, that's the most scientific way of doing it, or Windsorizing it. Okay, but here I just because I was kind of 성지급해, kind of wanted to see fast about how things look like. Okay, I wanted to drop those EPS growth rate bigger than 2. Okay, outliers, just drop it. Okay, remaining part I'm going to work on it. So for that purpose, I created regress 2 data. Okay, filtering function, and then I will do regression of PB ratio on EPS like this, and then summary of PB fit will be shown over here. Okay. The dependent variable is PB ratio, the raw PB ratio, before taking natural log. You see the result over here. Okay. Over here, what do you see? The t statistic of your explanatory variable is 1.7, and that means it's statistically significant at 10% level. You see, we confirm a positive relation, positive association between your PB ratio and expected net income growth rate over here. Okay, like this, right? But that's when we run a regression with the the PB ratio, raw PB ratio. What about, okay, so EPS, right? Yeah, and then what about log regression? Take a log of your dependent variable PB ratio and then regress it on EPS growth rate. Okay, you see t statistic being 1.66 for EPS, the coefficient. It is statistically significant at 10% level. Okay, we see confirm a positive association between these two variables, right? Of course, is it really significant? And I cannot say that, right? It's only 10% significant level, right? So that's why we're like, okay. Now, after taking natural log, we see more symmetric distribution of this PB ratio, and the result is weaker. What does that mean? Well, the positive correlation, okay, is more driven by extreme outlier values, it seems like. Okay, it seems like when we eliminate those power of those extreme values, those positive correlation weakens, right, in this data. But that does not mean that the economic theory is nullified at all, right? The economic prediction, the theory, tells us that these two variables has to be positively correlated. Our data happens to be weakly supporting it. Okay, that's how I would explain it. And then, um, yeah, and then another thing you could try. Yeah. No. Based on this, right? Based on this, you can try some scatter plots like this. Okay, scatter plots. How does it look like? Yes. All those company names are showing up, right? Like this. How come? You know, in your homework, maybe your observations were clustered so much in a narrow zone of EPS being like less than 2 or something. And then you must have seen a lot, some scattered, widely dispersed observations in the extreme. But remember, I truncated or I just dropped those EPS being bigger than 2. So that's why I have more detailed observation over here, detailed scatter plots over here. Okay. Of course, this is kind of a more quick and easy way, not scientifically supported that much. Why does it have to be 2? Okay, but it's visually it is more, you know, useful so that you can identify some of them being overvalued, some of them being undervalued. You can pinpoint those guys, right? We can zoom it up. Uh, let's see if the graph generates bigger. No, it doesn't show up. Anyway, so that's something you can try. And this is with, what is it? The, uh, yeah, the EPS and then log of price to book ratio. You can do the same with raw PB ratio. Okay, and it looks like this, right? A lot more clustered down there. So that's something you can see, right? Yeah, you can see a lot of skewness, and then the PB ratio, the extreme value going up over there, a lot more sparsely distributed like that. Whereas when you take the log, this is in the log scale, so that you will see reasonably symmetrically showing up in the picture. All right, so that's something you could try. Another thing you can do is truncating it. Yeah. If we, okay, if we try it, okay, if we try the same thing, okay, without filtering like this, right? How did we filter out the 97.5 percentile truncation? Let's go up and borrow from there, all right? PB ratio seems like this guy, all right? So what? Yeah, apply it to here. Yes, we come down. Nah, not really come down. We come to here. Yes. Okay. Oh, yeah. Why did I? Right. Yeah. We truncated over here. But what I'm gonna do is this guy. PB regress. Okay. I'm gonna create right, genome. Yeah. So all right. So how do we take care of this, right? Um, I tried this method, right? Truncating at 97.5 percentile top, okay? For that purpose, in that PB regress data, I needed to needed to find out the mean and standard deviation of it. Okay, PB regress and mean and standard deviation, and then of those mean and standard deviation of PB ratio, and then the growth rate in EPS, right? So I needed to compute those things like this, and for that purpose, yeah, yeah, you get these numbers right from the bottom, and then use it over here in the truncation function over here, truncation. And then for that, we need to create, what is that? PB regress number 3 variable, okay? PB regress. For that, starting from PB regress, I needed to create PB3, right? PB regress 3, like this, okay? And then, yeah, whatever the PB regress numbers, the variable that is, truncate it, and then throw it into the PB regress 3, okay, PB regress 3 variable like this. So original data set and then target data set is different over here, okay? And then once we constructed these truncated variable, I want to check out the histogram of this, and you see that PB ratio is now 0 to 4 only, not 8 or something, okay? Way lower, and then less skewed. And then EPS, again, right? It goes until 2.5. Before I truncated at 2 arbitrarily, but I was not too far away, right? So that's another thing I wanted to, just to highlight. This is more scientific, by the way, so follow this. Anyway, so profit, PB fit, right? PB fit, run a regression, and the result shows like this. If you regress PB ratio to EPS growth rate, the coefficient is positive but statistically insignificant, right? Only 19% p-value, okay? So it's a lot weaker. And then if you run it with log, and then the significance is even weaker, okay? The positive direction is there, but it is weak, statistically speaking. A lot more noisy, okay? So that's what we can find. And then plot it, okay? Log of PB ratio plotted using this truncation. Why doesn't it show? Remove the 63 rows containing non-finite values. So there is an error, right? Must be either length 1 or same as the data 200. Regress number 3. Oh yeah, come on, number 3. Yes, it has to be there, and then has to be like 3 over here. Yes, you see that, right? Yeah, you see that blue line? Is that 0 or not, right? The tiltedness, the slope term, okay? Can we safely say that the slope is non-zero, positive, or it can be negative, or it can be 0, right? We cannot reject the null that the slope is 0. So that's why we have this very low degree of tiltedness over here. The confidence band of it even goes to below 0, right? Minus. You see that. So that's why we don't have statistical significance, right? And if we switch it to raw PB data, okay, it will look like this. A lot more, a little more, not a lot, slightly more positive, but it's not that significant. So that's about it. Okay. I hope you enjoyed this part, right? But again, we usually hope that this regression line is significantly positive. And then we want to find out, identify those investment opportunities outside this confidence band, but this time the data happen to be, in a weaker setting, so that we are not able to firmly identify, we are not able to confidently identify those investment opportunities. But still, those high PB ratio, low PB ratio guys, you can also, you can still find out, split the sample into high growth rate and the low growth rate companies, half and half, and then high PB ratio and low PB ratio. You can split into 2x2 matrix somehow. That's non-parametric approach, right? Something like, I should say, something like this and that, right? So high growth, low growth, and then high growth, low growth, low growth but high PB ratio. This part, something fishy, right? Maybe more in a bubble, short sell it. High growth but low PB ratio, this group over here, you can suspect that it is undervalued. That's non-parametric way of identifying investment opportunities, but a lot weaker, less scientific, right? So that's the drawback. Anyway, another thing is you may want to run regressions based on same industry, okay, same industry, or similar kind of, companies. There, the other economic characteristics are controlled, right? Whereas here, we can still run it like this, okay? Identify some opportunities, but there are a lot more is going on inside each company. Their economic characteristics may be different, okay? That we could not differentiate or control here, okay? So that's a limitation over here. Okay, that's about it for this week, and I hope you like my lecture, even though it was a lot more bumpy, but I hope you liked it. Okay, see you next week. Bye bye.